Hello. Today I'm going to introduce Babylon geometry and Plimpton 322. Um, my name is Junyan Chen. I'm a math major, junior student. Uh, so I was assigned to this topic. At first, I was really confused about this topic because I barely knew Babylon before I do this research. And also, I was thinking, what is Plimpton 322 and how would it connect it to Babylonian geometry? I have solved those confusions during my research, so now I'm going to share it with you. Thanks for your understanding and patience. Let's start it. Uh, okay, so at the first page of my PowerPoint, I put two pictures. On the left, um, it's a stone. It has some rectangular on it. And if we look more clearly, we can see some Mesopotamian numbers on it. And this stone was found in the region of ancient Babylon. And if we translate those numbers into Arabic number, we can find that um, this stone uh, um, this stone these numbers means the length or something else uh, about the rectangular on the stone. So I selected it as a representation of the Babylonian geometry. And on the right, um, it is the Plimpton 322, which I'm going to talk about more later in this lecture. So at first, people thought that um, in ancient Babylon, people did not consider geometry as a thing. People used to think that Babylonians do not think that geometry is important because people think that for those ancient Babylonians, all they need to do with geometry is about their city plan, like this square, this place is set as square, and that place was set as rectangular. Um, People thought that they do not touch many important or not important, I mean hard stuffs about geometry. However, in 2016, the German mathematician whose name probably I cannot pronounce it right, but I will give it a try. His name is Matthew Osindri Jabbar. He discovered that actually ancient Babylonians used geometry quite well. How? Um, so this German mathematician, Matthew, he was translating some clay tablets which were found in the region of ancient Babylon. And he also do some research after he get them translated. So in 2016, he found that ancient Babylonians can predict the movement of stars and planets. So he said that the ancient Babylonians, they can predict the movement of moon, they can predict the movement of sun, but which kind of easy as long as people pay attention and have some accumulated data. However, Matthew found that the ancient Babylonians can even predict the movement of Jupiter. they discovered the Jupiter and used some geometry and algebra to predict the movement of Jupiter. That is totally out of people's thoughts, because people used to think that the ancient Babylonians do not use geometry really well. However, using geometry in some other subjects can be a proof that the ancient Babylonians really know about geometry, because using a subject into another subject has to be based on the freely use and quite well knowledge about the former subject. So we can, from those clay tablets research, we can know that ancient Babylonians knows geometry really well. And also, from some other research, we can know that Babylonians actually knows a lot about geometry, because they invented 6 decimal system, and they also divided the circle into 360 degrees, which is used until today. We can know that the ancient Babylonians, their empires were about 3,000 or 4,000 years ago from now. But some knowledge discovered at that time, or some technique discovered at that time, we can still use it today. That's really a thing. And so we get the conclusion that Babylonians knows geometry quite well, and they use them, and they invented some techniques that we are still taking advantage of it. Actually, I didn't find much information about the Babylonian geometry. So I'm going to talk about more about Plimpton 322. I found a lot of interesting stuff about it. Let's say first, what is it? So Plimpton 322 is a Babylonian clay tablet. It was discovered in the region which is called Saqqara. It was located in southern Iraq, and based on some other research, we can correspond it to an ancient city of Larsa. And also, it used Mesopotamian numbers on the clay tablet. So as we can see in the first page on the right side, those numbers, as we learned these days, they are Mesopotamian numbers, and they are in 6 decimal system. We also learned that this week. So why is it called Plimpton 322? Actually, Plimpton is a collector, and his collections are at Columbia University. This clay tablet was numbered 322. So Plimpton bought it from somebody who discovered the Babylonian clay tablet. So people just call it Plimpton 322. Yeah. And after some research, like comparing it with some other clay tablet found in that region, people were sure that this clay tablet must be made in 1800 BC, which is like 3,000–4,000 years from now. That corresponds to what I said in Babylonian geometry. And if we look at this clay tablet, the Plimpton 322, we can find that there are 4 columns and 15 rows. That's what it has. That's it. So at first, people thought Plimpton 322 was some business account book. So people didn't research it deeply, especially thinking about it from the aspect of math. However, after some research, like in 2016, people finally found out that this clay tablet has something related to math, and it's really well developed. So we can see that people are always correcting themselves. So maybe what we know now is not correct, but someday later we found out that, oh, this is not correct. Maybe something else is correct. So never believe what we got right now. Let's get back to Plimpton 322. Yeah. As we can see on the picture, some of the clay tablet was broken, like the first few rows of the first column and the fifth and sixth column, and the fifth and sixth row of the fourth column. But this doesn't stop us from researching it, because we can translate it. As we already know, the ancient Babylonians used Mesopotamian numbers, which are sexagemal system, and we translate them into Arabic numbers, which is widely used today worldwide. So what we got is this chart. So easily, if we can, and this picture is really clear, so we can look at it correspondingly. But now we're going to translate the sexagemal system into decimal system, and we found something more interesting. Oh, by the way, on the fourth column, it's just the row number, so it almost stays the same, 1, 2, 3, 4 to the 15th. Okay, after the translation from sexagemal to decimal, we got those numbers. At first, if we look at those numbers, we might not think about something at first. However, as I wrote in my earlier presentation, the Pythagorean triples, which is a squared plus b squared equals c squared, it has a lot of geometry meaning, right? A really important thing in geometry. So in the second and the third column, we can find such a relation of those numbers. Let's get back to the Pythagorean triple, which is a squared plus b squared equals to c squared. And if we move the a squared to another side, we can easily get c squared minus a squared equal to b squared. And then we can take in the numbers on the tablet into this formula. So let's take the first row as an example. So in the first row, on the second and the third column, we have 119 and 169. We take it into this formula, we can easily get 169 squared minus 119 squared equals to 120 squared. And that's not a coincidence at all. If we take in some other columns numbers of other rows into this formula, we can easily get another number. And let's see, for the second row, if we take into those numbers, the 3,367 and 4,825, if we take them into this formula, we can get 3,456. But is it really that simple about this clay tablet? Oh, so it's just some Pythagorean triples? No, not at all. Actually, if we do some other change on the formula we used, we can use m plus n to replace c, and we use m minus n to replace a, and 2mn replaces b. There is a condition that m should be bigger than n. So two more steps. The first step is we write a as m squared minus n squared. We write b as 2mn. We write c as m squared plus n squared. Then, finally, we can get to our last step, which we can write out m and n individually. So m squared is a plus c divided by 2. N is b divided by 2 divided by m. Now, we can have m and n as long as we have a, b, c. Some people might ask, why would we replace a, b, c as m and n? Because we have already knew that the Pythagorean triples are infinity. And how did we prove that? This is how we prove that. So we use m and n, any numbers which any number sets which m's are bigger than n's, we can have a unique Pythagorean triples. So if we take in those numbers on tablet, for example, let's continually use the first row into the example. We can get 119 plus 169 divided by 2. We can get m equals to 12. And if we take m equals to 12 into the formula to find n, we can find n equals to 5. And the same thing worked for the second row. As I mentioned before, this is not a coincidence at all, because if we have enough time and we can take in those numbers and give it a try, like today we have calculators, it is really easy for us. And we can find out that those numbers meet the definition of Pythagorean triples. That is really interesting because in the ancient time, people do not have many calculators like us today. So we would thinking, why? How would they do that, and why would they do that? Because so for the first question, why would they do that? We can find some. So look at the Plimpton 322 clay tablet. We can find some errors on it. why would there be errors? So people think that it might be some, so people think that this clay tablet might not be the true copy of Plimpton 322. People think that this clay tablet might be some copy from some copier. So why would this copier copy this clay tablet? People guess that the copier might be some teacher, or some people try to share this information to someone else. So we can, from this point, we can guess that in ancient Babylonians, teachers in the school might be teaching Pythagorean triples, and this is an example for them. So that's really interesting. Okay, I guess that's all I need to say about Babylonian geometry and the Plimpton 322. I hope I have give some interest for you about Plimpton 322 and the ancient Babylon geometry or mathematics. Thank you for watching. Bye-bye.